Hey, welcome back everybody to the next episode of FP 101X. And today we're going to talk about recursive functions. Well, what is recursion? Well, I have here a stack of trays and my favorite fruit. By now you all know that I love bananas. And I need to eat this a whole bunch of bananas. And if we're going to do this recursively, so we're going to eat the first banana, and then, but before I do that, I need to eat the next banana. So I have to put this one on top of this tray, and then, I have to eat the next banana. My goodness, I'm eating a lot of bananas, and look at that stack growing there. Next banana, and finally, I have my last banana, and I can put it on the stack. And look at this, a beautiful stack of bananas. See if we can see them. Now, the problem is that what we have done here is we have created quite a large stack of bananas. And if we would have a big bunch of bananas, that stack would overflow. So a better way to eat the bananas is to not start with the next banana until you've finished the first one. And in that case, you only need one tray to finish all your bananas. And that is called tail call elimination. And tail call elimination is a very important concept when you're using recursion to define control structures. And in imperative languages, typically, you don't have tail call elimination, and therefore, you have specialized control structures. But in Haskell, we can safely define our control structures using recursive functions because we will never have this giant stack of uneaten bananas. Great, let's look at some code. Enough, I think I have had enough bananas for the rest of the year. And the reason Haskell folks love recursion is that it's often a very natural way to define functions. For example, here's a way to define the factorial function. So here's we have seen this one before. So we take the list of values between 1 to n, and then we multiply them all together. If we are going to evaluate this factorial 4, we unfold the definition. That was product 1 to 4. The list 1 to 4 is product 1, 2, 3, 4. And the product was just kind of multiplying all the numbers. So there you see the product of 1, 2, 3, 4 is 1 times 2 times 3 times 4, which is 24. Here's a way to define factorial using recursion. And we have seen how to define recursive functions over lists and by taking the list, checking whether it's the empty list or whether it's the head followed by the tail. And in some sense, this kind of recursive function, the recursive function over numbers, is nothing different. So we have two cases. We have the fact whether the number is 0, or in this case, whether the number is n. And in that case, the recursion will be on n minus 1. And in previous version of Haskell, there were so-called n plus k patterns where you could write the factorial of 0 and the factorial of n plus 1. But n plus k patterns have been deprecated, so now we'll have to write it in this form. But apart from that minor detail, what you can see is that it's very, very similar to the way you define recursion over lists. There's two cases, 0 and n, and if it's 0, it's 1, and otherwise you just take the factorial of n minus 1 times n. And if we evaluate this form of factorial, you will see that stack of bananas appearing, because you see that there's the factorial going to the right until we have executed everything, and then we multiply going back, popping off the stack to get back to 6. All right. The recursive definition that we have given, of course, will not terminate, or a fancy way to say that is it will diverge for numbers less than 0. If we look here, let's go back a few slides. If n is less than 0, then we just, then this case doesn't apply. So we multiply n with the factorial of n minus 1, which is even more less than 0, and so on and so on. So this will never terminate, and it will cause a stack overflow. So some functions, like factorial, can be defined either recursively or defined in terms of other functions. And whether you define something using recursion or in terms of other functions, or you take this recursion pattern and abstract it as a higher order function and then use it to define another function, that's all a matter of taste. In the end, you decide as a developer what is the most readable for other developers. All right? So there's no strong answer when or not to use recursion. The code just has to be as clear as possible. But one advantage of recursion is that you can use induction to prove properties of your function. Let's look at another example of defining a recursive function where we're using this product function that we used in the earlier definition of factorial. And let's define that using recursion over lists. So in this case, the structure is exactly the same. There are two cases. We either have the empty list or we have a list of n cons n's. So we look at the recursive structure of lists, and then we define the function over that recursive structure. And the same with numbers. We look at the recursive structure of numbers, and then we define the functions kind of according to that structure. So in this case, if we have the product of the empty list, well, that is 1. If we want to take the product of a value n on top of a list n's, what do? We take the product of the rest of the list here, and then we multiply that by n. All right, so this is a very easy way to define this function using recursion. And of course, as we will see, we can take this function and abstract the pattern into a higher order function that just does the recursion, and then we can plug in the times and the 1. But if we execute this product, we unfold the definition. So it's like 2 cons 3, 4. So if we unfold that a couple of times, you get 2 times product of 3, 4. We do that a couple of times until we arrive here, and then we pop the stack to get 24. All right? So you see that the answer is exactly the same as the recursive definition of factorial. The only thing is that in this case, the recursion is hidden in this product function. So if we take the product of the numbers 1 to n, really we're defining the function using recursion as well. And you can show that when you fuse these two functions, the function that creates a list from 1 to n and the product function, that what you get is effectively the recursive definition of factorial. Good. Let's look at another function that we can define recursively over lists. And here you see, again, we have this, the recursive structure. So if it's empty, the list is empty, well, the length of that empty list is 0. And if the list is not empty, we don't care really what the first element is. We compute the length of the rest of the list, and just add 1 to it. Super obvious. Again, it follows the recursive structure of the list. So it's kind of defined by induction on the structure of the list. So length of 1, 2, 3, 1 plus length of 2, 3, unfold, 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 until here, and then we add them up and we get the answer that we expect, 3. Here's another function, reverse, empty list. The reverse of the empty list is empty list. And if we want to reverse x cons x's, we just add x on the other side. So if we execute it like this, you see that we're appending the elements from right to left, and then the list gets reversed. So 1, 2, 3 turns into 3, 2, 1. Of course, we can also define recursive functions that don't recurse over just one argument, but over several. We have seen in the previous chapter the function zip. And how do we define zip? Well, zip took 2 lists, and it would take every element of the 2 lists and combine them into a pair. So easiest thing here is to look at the last clause here. So if we have 2 non-empty lists, we take the head of both, put that in a pair, and recursively zip the rest. Now, when do we stop? Well, we stop when either of the 2 lists is exhausted, in which case we return the empty list. Okay? And of course, we have to put these cases first here, because there's a wildcard pattern here that would otherwise not work. Good. A few more functions. Drop takes an integer and a list and returns a list. And what this thing is doing, it's recursing over both the integer and the list. So in this case, when we say we want to drop 0 elements from a list, well, that's the same list. If we have the empty list, we can drop whatever we want, but we won't get very far, so we just return the empty list. And otherwise, we recurse both over the list and over the number. And again, since we don't have n plus k patterns, we have to use n minus 1 here on the right-hand side. So drop of n and whatever cons x's is drop of n minus 1 and x's. So here we recurse over the structure of the number and the structure of the list. The last example here on the slide appends 2 lists. If I want to append the empty list to another list, that is the other list. And then if I want to append a list x cons x's to a list y's, well, what do? I first append x's to y's, and then cons x on top. Super obvious. Thank you so much, and see you in part 2.